start recording. All right, so this is for RNase A. So here we have our upstream and our downstream pieces of RNA that are connected by a phosphodiester linkage. So remember what our phosphodiester backbone looks like. We've got our ribose sugar. Remember, this is going to be RNA, so this is an OH group here. If this was a hydrogen, this chemistry would not work, which is why DNA is so stable. So then we're going to have an oxygen, a phosphorus that's doubly bonded to an oxygen, singly bonded to an oxygen here. That's our phosphodiester linkage to sort of continue down here. So here's what we have here. In our enzyme active site, we have two important histidine residues. The native state for histidine 12 is deprotonated. The native state for histidine 119 is protonated. Histidine is one of those important amino acids that, because its pKa is near neutrality, it has the ability to be both an acid and a base fairly easily. Okay, we also have water here. We're not going to see water just yet, as we see in a general theme when we do these kinds of enzyme catalyses. What we're going to see is chemistry happen on the substrate in sort of the first act, and then the second act is going to have the use of water, and then that water is often what regenerates the enzyme active site. Okay, so first thing that we're going to have here is we're going to have histidine 12 acting as a general base, serves to deprotonate the 2' hydroxyl of our substrate RNA, okay? And that increases its nucleophilicity towards attack on the electrophilic phosphorus of the phosphodiester bond. So what happens there when we have this nucleophilic attack, we're going to move these pi electrons up, and we're going to generate what's actually a pentacoordinate intermediate. We're going to decompose that intermediate, and we want to break a bond to a good leaving group. Now, we could break this bond here, but that would just get us back to our starting material. So what we're going to have is we're going to have the phosphodiester bond break. Now, one of the things that we know is that the bond that is most easily broken is going to be the one that's most labile, and we can make bonds more easily broken and make leaving groups better leaving groups by protonating them. So that's where histidine 119 comes in. Histidine 119 is going to come in. It's going to act as a general acid. It serves to, in this case, protonate the 5' hydroxyl. Remember, this is the 5' hydroxyl group of the downstream RNA, facilitating the cleavage of that phosphodiester bond. So if we flip over here and we see what we have at this point, remember, when we formed this bond here, we generate what's called a 2', 3' cyclic intermediate. Now at this point, if we look at what we have, we can see that we've done chemistry on the substrate. We broke our phosphodiester bond, but the other two things that we have to happen, we need to use all of our reagents, so we haven't yet used water, and our enzyme active site is not properly created. Histidine 12 is supposed to be deprotonated, it's protonated. Histidine 119 is supposed to be protonated, and it is deprotonated. So water being able to diffuse into the active site, so we're going to have this guy diffuse out of the enzyme active site, allowing water to diffuse in. So water is going to be used to regenerate the enzyme active site and finish sort of the chemistry on our substrate here. So we're going to start now here with histidine. Histidine, now acting as a general base, serves to deprotonate water, okay, making it a better nucleophile for attack on the electrophilic phosphorus of this 2', 3' cyclic intermediate. Just like we saw before, when we have nucleophilic attack here, we're going to move these pi electrons up. We're going to generate a pentacoordinate intermediate. We're going to decompose that pentacoordinate intermediate. And now what we'd like to see break is this bond right here, okay? We're going to facilitate this bond breakage by histidine 12 now acting as a general acid. It's going to protonate this 2' oxygen, and that's again going to facilitate the breaking of that bond. We've made it be a better leaving group. So I'm going to flip over to the next slide just so we can see where these pieces sort of come into our final structure. So that's the hydroxide that came in as a nucleophile, and then this was our protonated 2' hydroxyl that made for a better leaving group. And that's the chemistry of RNase A. We can see that we've regenerated histidine 119 in its protonated state, Histidine 12 is in its deprotonated state, allowing this to diffuse out of the enzyme active site, and the use of water has completed all 3 steps of our enzyme catalysis.